All right. Does anybody remember what we talked about last week? We had an example of the tractor axle. What else?
We did stress analysis.
We did some stress analysis. Why were we doing stress analysis? Because academically speaking, I own your butt. Okay. No, it's why were we doing stress analysis? What was the goal?
Determine if the tractor was being break or not.
Here, it was specifically looking for static failure. And the whole thing we talked about last week, we discussed the 6 different theories surrounding failure when it comes to static failure. So we discussed all 6 of those theories. We discussed the math behind them. We discussed some of the motives behind them, of why they were developed the way that they were. This week it starts to get a little weird. So if, huh? Yeah, but it just gets a little weirder. So here's a question for you. If you load a bar to 80% of its SYF, SYT, and then release it, is there lasting damage? What's your thoughts? What sounds like it seems reasonable? So I take a bar and I load it up and I'm close to, but I'm not really at this yield tensile value yet. Is there going to be some long-lasting effects? Now, number one thing to consider, if I draw out my stress strain curve, if you draw on a true stress strain curve, it looks something like that. Well, I guess.
That's the engineering.
Yeah, that's the engineering one. Thank you. Because that's true. Was that you that said that? Oh, she had a really deep voice. It sounded like Preston for some reason. I'm like, ventriloquism. Oh. This is the engineering true stress strain. If I draw it out here, we're only loading it to this value. So again, would you expect there to be lasting damage if we don't even get close to that SYT value?
For how long is it loaded?
Well, we'll say we load it and then immediately unload it.
No.
You would think it wouldn't have any damage, okay? And that's a very normal thing to think, because it's like, hey, it's not anywhere near this. But then we have to go back and look at everything we explained last week when it comes to fracture mechanics. That being that we assume, according to fracture mechanics, there are going to be microscopic holes and cracks inside the material. That grow when loaded. This poses a problem because it'll grow when you load it once. When we're talking static failure, you only load it once. And so it grows. But then it stops because you're only loading it once. Well, the next time you go to load it, it's now a bigger hole. It's now a bigger crack. It will, again, you expect it to grow. And so we end up with the idea that every time a material is loaded, you have to expect it's going to experience some amount of damage. Okay? This is the concept behind fatigue. Because we might see failure occur much lower than the yield stress. Okay, well that's problematic. The whole reason why we're doing stress analysis in the first place is because we want to try to identify when failure is going to occur. That's why we were doing the static failure. That's why there was 6 different methods. And now we have to add an extra level of complexity to it. How many times was the material loaded before we started to do our analysis? And this is why I said today was going to get a little weird. If you ask me, this is the most complicated topic in this course. Okay? It doesn't get harder from here. It's just applications of everything that we've covered up to date from this point out in the class. But this is a difficult concept, and it is something that does require a little bit of deliberate attention. Okay? If you don't understand stress analysis, you're going to struggle to understand static failure analysis. If you don't understand static failure analysis, you're going to struggle to understand fatigue. Every one of these concepts builds on the ones before it. Because every bit of it is trying to understand different modalities of failure. Static failure is the easiest kind of failure. Fatigue failure is no longer the easiest kind. Because we do have to take into consideration what is the history of loading on this material. Okay. Now in the real world, what's going to happen? There's 2 ways of doing this. Number one, let's say you were dealing with. Oh man, it's on my throat. Let's say you're dealing with a bolt, and you want to find out whether or not this bolt is going to be able to withstand a certain number of cycles. Okay. What you would do with that bolt is you would take one bolt out of an entire batch, and then you would start loading this bolt to whatever maximum stress you expect it to experience, drop it back down to 0, or potentially even put it in compression. You would load this bolt, and then you would see how many cycles it lasts. If it goes a full 100,000, if it goes a full million. Okay, and maybe you cycle it once a second or 5 times a second, something like that. And when you put it into that kind of loading, you can then comfortably say that you would expect most of the bolts in that batch to behave similarly. That's typically what we do. Okay, so physical testing is always going to be the best way of measuring fatigue. It always will be. There isn't another option that's better than fatigue testing. The only problem with doing fatigue testing is it just takes a long time. Because if you want to go through 1,000,000 cycles, how long is 1,000,000 seconds? That's a good question.
Couple of days, 12 days. 13 days.
Yeah, about 1.5 days, yeah. Nice.
I just remember that about 8,000 seconds in a day, and that it's easy to.
Yeah. Well thought. Andre's break. Clutch today. So it would take 11.5 days of full testing, doing 1 cycle per second to get 1,000,000 cycles. Okay? And that it just takes a long time. Now, what they would usually do is they would cycle it to 1,000, check and see damage, check stress, check residual strain, cycle it to 10,000, check stress, check residual strain, cycle it to 100,000, and so they end up doing it by factors of 10. And it is because what we've seen is that fatigue tends to have a logarithmic effect. Basically, it's the difference between 8 and 9 is substantial, and the difference between 1,888 and 1,889 is not. Okay, again, logarithmic importance there. So, physical testing is going to be your best way of doing it, but we need some kind of algorithmic way to try to predict fatigue failure. Why would we want to be able to predict it academically? Why would we want to be able to predict it using math?
Those are the machines that do the fatigue tests.
That's funny.
Yeah.
It's not wrong, but it's funny. Yeah, I mean, you gotta make sure that the machine itself works. Why else?
To save money and time.
Some of it is saving money and time. I don't want to spend 11.5 days cycling something to 1,000,000 cycles. Okay? And what happens if, Bennett, you're doing the cycling and you work 8 hours a day, but this thing's running for 24 hours a day? What happens if it fails in the 16 hours you're not there? Okay? Hopefully you have some kind of a mechanism for detecting that. Hopefully that's built into the machine. But you're not even there to watch it. You don't even know it's close. You don't know what happened right before that, unless you have a constant stream camera on it, in which case then you have to watch 16 hours of great fun. Although it shouldn't be that hard.
You find the time that it breaks, and then you just go to that time stamp.
Yeah, because you break it down into like fourths, and you say, okay, has it broken at halftime? Okay, if the answer is yes, has it broken at quarter time? You break it up like that. So yeah, you wouldn't have to watch all 16 hours of it, but you're still not there. This test is going on while you're not there, and predominantly it's going on while you aren't there. So there's a tremendous amount of desire for us to be able to say, I want to be able to predict this. I don't want to have to do the testing, and I sure as heck want to know what's going on with this. Okay? So we're going to have to introduce a number of different concepts as a part of discussing fatigue, because it's not as straightforward as static failure. Static failure, you compare stress to the yield strength, but in fatigue failure, we have to take into consideration the history of the loading, but also some additional pieces that go along specifically with the material. Because certain types of materials will behave differently when they're loaded cyclically. Okay? So, let's talk about a couple of considerations here. Fatigue. And I guess before we move on further, you do have an exam next week. It will give it to you on Wednesday. You'll have a week to complete it. If you've ever done an exam in any of my classes, it is entirely online. I believe it's like 15 questions or so. You will not be able to see the answers do the exam until after the exam is completed, but you will be able to see whether or not you got a question right. You have 2 attempts on this exam. So I would strongly encourage you, take those 2 attempts, do both of them, but they both must be done before the due date. I'm not going to be assigning you any homework for that week. Next Wednesday, we will not have class. Because I feel like on Monday we'll cover review, and then on Wednesday we will have class. So show up on Wednesday, okay? Make sure that you are there. Okay. We don't have class next Wednesday. I just wanted to say that was you know, coming into the room so that you were the only person that showed up. Oh crap, no one told me. But no, we're not having class next Wednesday because I'm giving you a test. Just be watching for that. I would encourage you, go back and look through your homeworks and make sure you are comfortable with how each of your homework assignments were done. If you are not comfortable with those homeworks, come talk to me after class, talk to your peers, get some help, go read the book, go work through the example problems, go ask AI, do whatever you need to do, because being comfortable with those problems means you will be comfortable with the content of the exam. I try to make sure that a majority of my exam is going to be either questions related to vocab quizzes, or things that you should have already encountered, or questions related to exam material itself. Now I do realize that canceling class on Wednesday means we are not having a vocab quiz over fatigue on Wednesday. That may not be the best way to do this. I just put the exam back on the day. I mean, I could, and then we could just not have Friday. I'm also going to be gone on the 25th. Oh no, that's not true. Yes, it is. It 100% is true. I will be gone on the 25th. So, I'm going to be at LES. So we will not have class that day. Yeah, so you'll be missing 2 days in 2 weeks of this class. That's awesome. Okay, but do be aware, the exam is coming. All right, when we're coming to fatigue, let's start out by talking about some things that people have noticed. All right, first things first. When we first discovered fatigue, it was because we were loading something repeatedly. You know, like if you go out and look at your playground equipment, if you have any bolts or something on playground equipment that is very well used, those bolts are usually rated to be able to handle those. You don't just jump on it and pops. But over time, the bolts on it kind of break. At least they did on my jungle gyms when I was a kid. I also beat the crap out of those things because I was playing on them all the time because I wasn't allowed to watch TV. So, you will see that there are times when they break. Now, in loading something repeatedly, having something jumped on, having a machine vibrate constantly, what we were noticing out of our fatigue failure is that if I have a bolt and this bolt fails here due to fatigue, usually what it looks like is something like this. Okay? Now, do you remember when we talked about the different stress, there's words. Yeah, the different static failure theories. There were two different kinds of static failure theories. Do you remember what they were? Ductile and brittle. In ductile failure, we expected things to break at a 45-degree angle. Which, interestingly enough, resembles that. And in brittle failure, we expected failure to occur at a 90-degree angle, basically parallel to the plane. Which, interestingly enough, is that piece. Here's the thing. What we're seeing out of brittle failure is that there is, because this is loaded and unloaded, we're seeing a very dull surface. This causes metals that are normally very ductile to ultimately fail, just simply snap at something that's lower than the yield stress. Okay? Nowhere close to the ultimate stress. It just snaps. And what happens is, as it snaps, this little piece, which probably didn't experience a whole lot of fatigue stress during its life, is basically ripped apart. Because it has to carry the entire load of everything now as this entire thing fails. So it's not uncommon in fatigue failure to see a mixture of brittle and ductile failure at the same time. The brittle failure happens because that's where failure happens first, and the ductile failure happens because that's where it happens last. Okay? Now we often can't predict what that profile is going to look like. But we do know that it tends to be it looks the same way as what we have when we have a bolt and you freeze it in liquid nitrogen and then you load it to failure. It looks the same way there. Okay, so not shockingly, fatigue. When we talk about fatigue, what we're specifically referring to is the brittle failure piece, because the ductile failure piece oftentimes is more guided by static failure. So, okay. So when I say that brittle failure is what causes, it's because that's the mechanism of fatigue failure. Is that brittle? So, okay, what kind of factors do we see cause this? We see different types of behavior out of different types of metal. Cast iron has a different fatigue quality than what you're going to see out of aluminum. Aluminum is very different from steel. Now, we didn't have to differentiate between those three metals when we talked about static failure, because every bit of the differences there were just, what's the yield strength? What's the yield strength? What's the yield strength? You go look up the yield strength for steel. You go look up the yield strength for aluminum. You can figure out where it's going to fail. This one, the type of metal actually determines how it's going to handle fatigue. We'll get into this in the next class, but steel tends to handle fatigue the best out of all materials. Aluminum, not so much. In fact, aluminum tends to, it doesn't handle very high loading values. You can make any piece of aluminum fail if you load it with enough stress over enough time. we may be talking about trillions and quadrillions of cycles if the stress isn't large enough. But still, you can make any piece of aluminum fail. And that is not true for steel. As I mentioned, this type of failure was very similar to seeing it happen in liquid nitrogen. Well, it turns out that temperature is also a factor. Okay? It turns out the geometry of the cross section also matters. So as people started to see these things, they were saying, oh, okay, this causes a different type of failure. This causes fatigue failure to occur at different rates. Then they started doing different type of loading. You have machines that will put an object into pure bending. And they were seeing that machines that were putting them in pure bending were failing at a different rate than machines that were putting them in pure tension. Okay, so that affected it. But and then what we also saw, looking at this, is that we talked about different methods for getting a surface treatment on the outside of the material, like quenching, like doing annealing processes. Turns out those also have an impact on the fatigue life of these metals. So not only do surface finishes, but heat treatments do too. Okay? And now, Alex, you said the reason why we want to do this is because we want to save time. Now we're starting to get into really ugly territory. Okay? I told you at the beginning, you cannot beat physical testing. You do physical testing, you save this entire chapter. You do physical testing, you can even save the last chapter too, as long as you know what you're doing. As long as you understand that you're testing for static failure. Okay? Any kind of tensile tester, which is what you're designing for your senior design project, that is testing static failure because you load it once. And as long as you understand how you're causing things to fail, you can identify some of these pieces when you go to do the testing itself. But now, with all of these differentiating factors being at play, in order to do an accurate test, if you're going to have a bolt holding up a piece of playground equipment, you're going to have to make sure that it is, oh, and I forgot corrosion. You're going to have to make sure that that bolt is at the kind of condition that you would expect a real world bolt to experience. You have to. Otherwise, your testing may not be accurate. And so that's another piece. It's not just about saving time, it's also about now we can just try to predict things that we may not be able to simulate well inside the lab. Yeah.
So if you add a washer to the bolt, would that be changing the geometry, or how would that change it? That would help it.
It does because it distributes the load across, and it prevents there from being specific pinch points. And I would say it more changes the type of loading, because you may end up with less shear and more tensile load with a washer, whereas without a washer you may end up with more shear and less tensile load. Okay, that was a good question though. All right, so now that we know that these are some of the factors that play into fatigue, the whole goal of doing a fatigue analysis is to identify, so in static failure, we were looking for N.